Good evening, sir.
Hello.
Yeah, good evening,
Good
sir.
evening, to all.
Good evening, sir.
Yeah, good evening.
Good evening, sir.
Okay, today we will start with the column design, basic concepts and manual calculations. Okay, and then we will discuss the Excel program design. So last time we have taken the footing design. So today we will take the column design. So, what kind of forces comes in the column? Anybody from you? What are the forces which come in the column?
Axial force
Yes, so there may be axial force and
and biaxial moments also.
so in any structure, in building especially, kind of this 3D structure, there are loads, all of you know. There are loads on the beams due to slab and walls and their self weight, whatever. What happens, there is a bending moment in the beam, and as we consider these joints as a fixed joint or rigid joints, there will be the fixed end moments like this, and these fixed end moments will transfer in the column also. So this whatever beam moment is there, it will, whatever unbalanced moment is there, it will transfer in the column. So there will be moment here, moment at top and moment at bottom also in column. And whatever shear force is coming from the beam. So all of you know that how this vertical load will transfer in the column. Maybe in this case, half will be here, P by 2, and half will be in this column, P by 2. And then again, there will be bending moment due to these fixed end conditions. Apart from that, as you know that there is beam in this direction also. So this beam also will have a bending moment like this. And this bending moment will be in this direction. So the directions are different actually. So it's a biaxial moment, we can say. One on, let's say, if I, so this column is nothing but a cross section like this. And if this is a column in plan, if you see, then there will be the moment about x axis and say. So if you see this Z, what we can say, this red color moment. So this red color moment is nothing but, if you see this, this is the plan, and this red color moment is nothing but this moment about this axis. Okay, this one. And this blue color moment which you can see is nothing but about this axis, right? So if you consider this axis as a x axis, this axis, and this vertical is a y, so you can say that the red color moment is nothing but my, and this blue color moment, whatever you see, is a mx. So this is the general, we can say, behavior of the columns and forces coming in the columns due to the loads. And we get these forces from the ETAP software or STAAD software, whatever you use. So we get from the model the axial force P, or generally we design columns for ultimate loads. So PU, then we get MUX, moment about x-axis, MUY, moment about y-axis. That too at top and at bottom. You can see this is a top and this is a bottom of the column. Okay. Similarly here, MUY at top and bottom. Okay. So this is the general behavior. Now, if you now we will do one thing, we will ignore the moment and let's calculate the capacity of the column. Let's say you have a column size. We are designing a column, we can say. So whenever we design, what we do, we calculate actual stresses and we check it with the permissible stresses given in the code. And this is nothing but a design. So whenever we say any design, design is nothing but calculating actual stresses and comparing with the permissible stresses. And if your actual stress is less than permissible stress, your design is okay. So this is general philosophy, we can say. Or whatever you calculate actual force should be less than permissible force. So you can get, and you get these permissible stresses in IS code. So in our case, we are using 456. Now let's say column size is say 200 by 500. And we are putting steel into the column as let's say 16 mm diameter, 6 numbers. So tell me, what is the capacity of this column? How much maximum axial force it can take? Axial capacity of column. Anybody? P
0.45 FCK AC plus points.
Yeah, so
0.5.
0.4, let's say 0.4 FCK and BD, right? Plus, so this is your concrete
0.67.
capacity. This first part. And second part is 0.67 Fy into
Fy ASC.
ASC. Okay. So Fy, let's say 500 Newton per mm square, and FCK is, we can assume as a 25 Newton per, that is 25 MPa, grade of concrete. Okay. Now this is your concrete capacity and this is your steel capacity. So what will be the capacity? 0.4. So see, what is this 0.4 FCK? This part is nothing but permissible stress. Yes. And this is the cross-sectional area. So permissible stress into cross-sectional area will be force. That is the capacity. And this permissible stress is in concrete material. And there is this permissible stress, it is in steel material. And this is a permissible stress and this is the area of steel. So all of you know that whenever there is a load on the column, so whatever bars are there within the columns, let's say we are having 1, 2, 3, 4, 5, 6. So the force or whatever compressive load is there, it will be taken care by the concrete within this and the steel. So it will be 0.4 into 25 into 200 into 500 plus steel part is 0.67 into 500 into AC 6 numbers of bar and 16 mm diameter. What is the area of that? Almost 201. So this part is, how much is this? So you will get the answer in Newton. So you can convert that into kilonewton also. So how much will be this? 10,000 kilonewton. Yes or no?
Yes, so 10. It will be 1,000.
1,000 kilonewton. Yes. And for this steel, it will be 400 something.
Yes, sir. 404.
404. Okay. So this 1,000 will be give say 1,000 is the capacity of concrete actually of the size of 200 by 500. Okay. And this 404 is the capacity of these reinforcement bars. So we get final the capacity as 1404 kilonewton. Now, if your column is having axial force, compressive force less than this, then this section you can use. Okay. So this is a general gravity, we can say, design for columns. But in reality, we don't have a column which is carrying only axial force. It also carries bending moments. So that is MUX and MUY as I said. So what happens due to the bending moment? So here, what due to the axial force, what we get? So due to the axial force, we are having axial stress. in the column, which is nothing but Pu upon A. I can say this is a sigma AC axial compression stress, axial compression, and due to bending moment, there will be bending stress, which is nothing but M upon Z. So if this M is MXX, then MXX upon ZXX. So let's say I would sigma BX and sigma BY. So bending moment about Y, MYY upon ZYY. So there will be additional stresses, additional bending stresses. So all of you know that it is a P by A plus or minus M upon Z. This is the
Yes.
general combined stress, we can say, in the column, as we have done in the footing also. It will be same for, see, bending plus axial compression will be same philosophy. Either it is a footing or it is a column or any other members like that. Okay. So there will be additional stress, and then you need to design for that. And generally doing it manually is comparatively difficult. And the books have given the procedure codes, IS codes. So let's go to that procedure now. How to design the column for biaxial moment. So let's take one example where the concrete grade is M20, steel grade is Fe500. All of you know that cover to the column is 40 mm. Floor to floor height is 3 meter, let's say. Axial load 2000 kilonewton, which is coming from the analysis. And MUX is 65 kilonewton, MUI is 25 kilonewton. This is major axis moment, minor axis moment, and size of the column is 300 by 600. So this is our input. Let's say we get it from the analysis. Okay. So let's go by step actually. So unsupported, so we need to calculate the effective length of the column. So how to calculate the effective length? As per the code, page number is 94.65 L, and this L is nothing but unsupported length. So do you know what is meant by unsupported length? Unsupported length means by subtracting the beam depth.
Yes, sir.
So that is the unsupported length. Say, let's say if you have a column like this, okay, and let's say this is your beam, the beam which is resting on the column, and let's say this is your floor. Okay, this is your floor. So floor to floor height is, let's say, 3 meters, and this beam depth is 600 mm. Okay, so we are subtracting this 3000 minus 600. It is unsupported is 2400. So effective length will be 0.65 L, which is nothing but 1560. Okay. So generally now this is a theoretical value of 0.65 as per the code, but we generally in practice we take 0.85, because see, this is for full fixity, but in reality or practically we don't get full fixity on site as per the boundary condition. So we are generally taking little on the higher side, which is a 0.85 for practical purpose. So this is a fixed condition only, but we are taking little release or partial fixity, we can say. So 0.85. So this is the table which we know, and we are taking 0.85. Now we need to calculate the check for minimum eccentricity. So all of you know that whenever we design any column, let's say this is your column, and we assume that our axial load is exactly passing through the CG of the column. But many times it is not possible, because there is a possibility of eccentricity due to the inaccuracy in the plumb. So it is not necessary that your column will be exactly vertical on site. There may be possibility that it will have a little inclination due to the bad construction practice or due to the human errors. So that means there is a possibility that this force will not be exactly passing through the CG of this axis of this column. It will have some eccentricity. So it is something eccentric from the CG, this line. So this E is there. So we generally design the columns for minimum eccentricity. And this E minimum is calculated as per the code given. These are the clauses, page 42. Ex is nothing but L upon 500 plus D by 30 or 20 mm, whichever is maximum. So L upon 33,000 divided by 500 plus 600 divided by 30. This D is nothing but our dimension. So if this is the column and this is 300 size of the column, this is 600. So if you are considering this direction, X direction, let's say, then what we are doing actually, we are taking eccentricity like this. Let's say this is your point and this is your Ex, okay, in X direction. And let's say vertical axis is Y. So Ex is nothing but this L upon 500 plus 600 upon 30. So this 600 means these dimensions as you are taking the Ex in X direction. So so you are getting 26 mm. So we are taking maximum out of this 20 or this, whichever is maximum. Then we need to calculate the moment in X direction. So all of you know that due to eccentricity and the load is there, Pu. So Pu into E will be the moment, additional moment due to eccentricity. So that means we are adding the moments actually in column design due to eccentricity. So your eccentricity moment will be 2000. This is the actual load, I think, into this eccentricity, 52 kilonewton. So this is, yeah, so we are getting this from the analysis and this from the eccentricity calculation. So we are taking maximum out of this. Okay. Now, similarly over here, if you see here EY minimum, because in the other direction. So EY is nothing but on the other direction. Let's say this is your column. Horizontally tha kya pehle? Okay. Generally, we take the axis. Actually, this is the axis. I should have drawn it correctly. ये ऐसे होगा. Let's say if you say this as a y, x. So from here to here, we can say this is a y, ey. Okay. So ey is nothing but L upon 500 plus b by 30. So b is the 300 dimension. Okay. So in this case, you get 16 mm eccentricity and 20 mm. So you need to take maximum of this. So you are having a moment from analysis 25, and from eccentricity you are getting Pu into Ey minimum, which is 40. So let's take maximum out of these two values. So these are the two moments which we have got from the eccentricity check. Now, yes, now as all of you know that this is not a linear design of columns as we do. There is no only axial force, but there are moments in both the directions. So generally, whenever we design any column, we need to do the interaction of the column. So interaction means we are using different charts as per SP16, and we will use those for the design purpose. Okay. So let's see. Try to understand it first from the stepwise procedure mechanically. Only try to understand where to put what values and how to get the results. And all other things are similar as I discussed with you. This axial stress, this combined stresses, bending stresses, like that. But there are so long, as we cannot do this because it is we can say iterative process, and the answers, or rather the solutions for this column design will be complex to do manually. That's why code has suggested these kind of charts depending upon certain ratios like Pu upon FCKBD and Mu upon FCKBD square. So on that basis, we can do the design of the columns for biaxial moments. Now let's see how to do this. Yeah, so we already know that whenever we design anything, we need to assume certain things and then check for the stresses. So we don't know what percentage steel we are going to put. Let's assume that we are putting the percentage steel as a 2%, okay, in this column. So we need to calculate the cover, effective cover in this. So let's say this is your column, and there are reinforcement we are putting here in the column, like this. And we need to calculate the effective cover, D. So effective cover is cover plus stirrups diameter. So you know there is a stirrups here, plus longitudinal reinforcement divided by 2. That means I'm interested in to calculate this value exactly at the center of this bar. Okay. So what is this value? It is nothing but this D dash. So 40 cover plus 8 mm diameter of the stirrup plus this main diameter by 2. So 58 mm will be the effective cover, D dash. Now this PT is nothing but, I have assumed this 2%. So 2 upon FCK is grade of concrete. So it is coming 0.1 PT upon FCK. Then we will calculate PU upon FCK BD. So PU is from the analysis upon FCK, B is the column dimension BD. So we get 0.56. And this D dash is effective cover 58 divided by D, that is 600. So as you are interested in X direction, so we will take longer dimension. So generally this is the X axis and we call it as a major axis, and this is your dimension 600. Okay. So D dash by D. Now so what we have got, PT upon FCK, we have got PU upon FCK BD. Now there is a chart given in the SP16, chart 47. D dash upon D is how much? 0.05. Okay. So there are two charts. One is 0.05, second chart is 0.1, and our value is lying between the two, 0.097. So we will use both the charts. D dash upon D is 0.05 and D dash upon D 0.1, and we will interpolate the values between the two. So now chart number 47, D dash upon D is 0.05. So PU upon FCK BD, how much we are getting? PU upon FCK BD 0.56. So if you go over here, PU upon FCK BD is along the y-axis. So this is the 0.56. You draw this line horizontal, and this is your PT upon FCK value. These curves are for PT upon FCK, which is 0.1. So you can see this is a 0.1. So whatever, as it intersects to the 0.1. So this is the 0.56 between 0.5 and 0.6. This is your PU upon FCK BD you got. So you will go here, and this curve, whatever you see, it is for 0.1 PT upon FCK, this one, 0.1. Now I will just intersect this and take this down, and whatever value I get, this is my MU upon FCK BD square. So 0.105. 0.105. Similarly, I will go in the next chart for 0.1 value. 0.56, go till 0.1, this curve, go down 0.095. So you got two values, 0.105, 0.095, and my value is in between the two because D dash by D is 0.097 in my case. Okay.
Yes, sir.
So by interpolation, we are getting this value 0.0956. Okay. Between these two. Now MU upon FCK BD square. So MU is this ratio, whatever we have got. So this value you are getting how much? MU X upon FCK BD square. How much you got? 0.0956 from the graph and interpolation. This value is 0.0956 from interpolation. Then if you are interested in calculation of the moment, okay, so how much is this? This will go to the right side. So MUX is nothing but this ratio into this FCK BD square. So this is your moment. Okay. Now let's go to the next part. along y-axis. So we have done it for x-axis previously. Along y-axis, PT upon FCK 2 upon 20.1. PU upon FCK BD will be same. D dash by B. In this case, it is a B, not D. So 58 upon 300, which is 0.193. Now there are other charts also. Your value is between 0.15 and 0.2. So you will refer these two charts. D dash by D 0.15 and D dash by D 0.2. And the values are in between. So similarly, we have done this. And we have got this mu upon FCK BD square value as a 0.087. And you got mu y1 as 87. Okay. So this way you got mu x1, mu y1 from the charts. Now we are going to calculate the PU's head. So this is, we are generally calculating the capacities of the section. Huh? So we will calculate the capacities and we will develop this interaction ratio and we will check whether it is less than 1 or not. Okay. Now we have calculated mu x1, mu y1, the capacities. Now we will calculate the actual capacity, which is PU's head. So PU's head is 0.45 CKAC plus 0.75 FYAC. So regarding this, why it is coming, you will refer the books actually. We will have we shared the books, RCC books to you?
Yes, sir.
Yeah, so you can refer that book and you'll understand why this 0.45, why this is 0.75 and so. So 0.45 FCK, put the values. So AC here you can see, AC how much? FCK you know, AC you know, AC means area of concrete 300 by 600. What is ASC?
Area of steel.
Area of steel कितना है हमारा? 2% लिया है ना हमने? We have assumed as a 2%. So how much will be this?
Yes, sir.
2 upon 100 into 300 by 600. So here you can see 2 upon 100 means 0.02 into B into D. So this is your actual capacity. Now you need to calculate the ratio of your actual load and the capacity. PU upon PUZ. So this is 0.673. Now there is one term which is alpha n. So alpha n is given and you need to calculate this alpha n also. So PU upon, so see here, you can see here in 39.6 code for values of PU upon PUZ 0.22.8. So the ratio, see here, in between this, your value is getting. The values of alpha n vary linearly from 1 to 2. So 1 to 2. So if this ratio is from 0.2 to 0.8, the alpha n will vary from 1 to 2. As our value is 0.673 for PU upon PUZ, we are getting some interpolation. After interpolating, we are getting alpha n is equal to 1.788. So, and then why it is required here in this equation, we require in this 39.6 equation, MUX upon MUX1. This is from the analysis or from minimum eccentricity, whichever is maximum. So MUX is 65, MUX1, whatever we calculated from the charts, MUI from the analysis or eccentricity, and MUI1 from the chart, and alpha n is this 1.788. Your value should be less than 1. Then and then your column design is safe. So this we call it as an interaction ratio. As we are having biaxial moment and axial force, so multiple forces in different directions are there, and that's why we need interaction ratio. Okay. So now you got that this is safe. Now you go to the design. So that means I can say that your assumed steel percentage 2% is coming safe. So whatever you have done regarding the column design, it was based on the assumption of percentage steel, which is 2%. That means your design. Now you can put your this 2% steel in the column. So how to design the steel? ASC is 0.02. So calculate ASC 0.02 into this 3600. Assume some diameter of bar. Let's say assume 20 mm diameter of bar. So number of bars are area upon area, total area required divided by area of single bar. So let's say 12 numbers will be required bar in the columns. Now there is some other clauses regarding the stirrups. Okay. So for using the diameter of the stirrups, this is as per the code. It should be maximum of 1/4 of the diameter of the longitudinal bar. So 1/4 of longitudinal bar is 20 mm. So it is 5 mm or 5 mm, whichever is maximum. So generally we don't use 5 mm or 6 mm bars nowadays. We go with the 8 mm bars. Then now regarding the spacing of the stirrups or ties, generally we call it as a lateral ties. Minimum of least lateral dimension of the column. We know that our B value is 300 or 16 into diameter of the longitudinal bar, 16 into 20 mm diameter of bar, 320 or 300 mm, whichever is minimum. So in this case, it will be 300. So our bars are 12 bars, T20 diameter, and stirrup is 8 at 300. So this is, we can say, general procedure. So we are having 12, 20 longitudinal bar and 8 at 300 spacing. You might have seen the detailing like this. And this is the plan of the column section. So 12 bars are there, and lateral ties and everything is given. So is it clear to all of you?
Yes, sir.
Yeah, it's a mechanical procedure, we can say. We need to follow the code. Only you need to understand what you're doing within that and why it is happening. So this interaction is required because there are multiple forces, that is axial force, then biaxial moments. So it is not possible to design any section linearly using linear equations. So that's why this equation and that graphs are developed by the code, and you need to follow this. There is no other way. So all of you, please do the one of the manual calculation for this. Now one more point I would like to show you, that the interaction ratio is how much? 0.37. What do you understand by this interaction ratio? This means that you are using only 37% capacity. Okay.
So 30% ही उसका यूज हुआ है लोड का.
हाँ, बाकी 63 आएगा ना. हाँ, 63% unnecessarily ज्यादा जा रहा है. It is going more. That means your design is not much economical. That is the meaning of this. If your ratio is, let's say, 0.9, this ratio, and it is less than 1, then I can say you are using a 90% cross section. So the more is the interaction ratio near to 0.9 or getting near to 0.9, then it is your economical design. If it is less than 0.5, that means 50%, then it is not economical design. That means your force is 1000 and you are giving the section capacity as a 2000 kilonewton. It is not good design. Okay. As I have just shown you the procedure, that's why I have not done the iteration again. What can you do again? So as you have assumed the steel percentage as 2%. So as a matter of homework, I request all of you, please assume the percentage steel as a 1.5% for your homework. Okay. Practice, because now you can see that your 2% steel is more. It is actually not required. So some of you can assume 1.5%, some of you can assume 1% also, and please design this manually. Same problem. Okay.
Okay, sir.
Yeah. Now, as this procedure is laborious and manually it is, we can say, lengthy, it is important for understanding the concepts, but for practical purpose, if you do this by this way, it will take a lot of time to design the columns. Whenever there were no softwares, the structural engineers used to do by this method only. There was no any other methods. But now we have the methods like softwares or Excel programs. So let's say how to design the column by using Excel programs. Okay. Now, whatever is this procedure, it is inbuilt here inside this. So, very simplest method we can say. So, now we design the columns once we get the results from the analysis. And analysis is generally so all of you know how to see the column results from the ETABS? Hello?
Yes, sir.
Yeah, so you need to click the column, then go to the display, then force and stress diagrams, then go to the frame
Yeah,
peer
yes,
forces.
sir.
Okay, so
Yes,
once
sir.
you go there, then you will get so you will get this dialog box. So if you click on the this V2 and M3, you will get this M3. So you will get M3 moment here, which is 5.32. Oh, this is minus 5.32. So first of all, let's do one thing. We will design one column in which M3 is
Minus 5.3.
minus 5.3 kilo. Then M2, once you click over here, V2 and M2, V3 and M2, then you are getting this M2 value as minus 0.84. M2 minus 0.84.
4 kilonewton meter.
And then you get for axial forces here. Once you click over here, axial force P, which is nothing but 1288.8.
Minus 1286.
Okay.
1286, sir.
Okay, so whatever is the number.
Okay.
Then now you see here that here there are two values for moment. So let's say if you see the M2, then this yellow color and orange color is there. Because this is nothing but your top and bottom of the column. Okay.
Yes, sir.
Similarly here, there will be top and bottom of the column. Correct.
Yes,
So
sir.
there are two values actually, MU2 top and MU2 bottom. So for M2, there will be top value also and there will be bottom value also. Okay. So I'll do
Okay.
one thing. Now, have you got how to see the results from the ETABS first?
Yes,
Yes,
display.
Yeah. Okay. Now I will take arbitrary example. So I'm not interested in that for why? Because see, I have not taken that top and bottom values. Okay. So you got the concept how to get the results. Now see, let's say we have a column axial ultimate load on the column is let's say 1500 kilonewton. Then I have the value of MU3. Let me say 3. They all are M3 top, M3
Bottom.
bottom, M2 top, M2 bottom. Okay, so there will be 4 values for the moments. Let's say your M3 top is 40 kilonewton meter. So there, as your column values are like this, many times you get this kind of values. So there will be one value positive and one is negative. Okay. So
Yes,
you from the software you will understand. It may be top. So don't bother about that. Just let's say this is your 40 value and this is your let's say 20 kilonewton meter M3 value. So top it is 40 plus and at bottom it is minus. Okay.
Yes, sir.
Not kilonewton meter. Similarly, you have some that same column, but you are having the values let's say this is 15 at top and bottom is, let's say 10. This is your M2 value. So 15 and this is 10. You got this?
Got this.
Simple. Only that we are getting the values horizontally in the ETAP software. That's in the dialog box. So these are the values which are required for design. Now, in Excel sheet, actually, if you see, the axes are different. So the major axis is X and minor axis is Y.
Y.
So we need to convert that now, because Excel is designed with respect to the manual calculation and not with respect to the ETAP. So in, let's say this is a column or beam. You know that in ETAP, the major axis is 3, 3. Okay, major means, what is major axis?
X.
No. Major axis means what? It cuts the depth of the column generally. Okay, so if this is the depth of the column and if it is width of the column B, then the axis which is cutting this depth, okay, is 3, 3. That is major axis. And this is minor axis which is cutting the width. Are you getting?
Yes, sir.
Yes, sir.
So we call this Y as a minor axis and 3, this, not Y, I need to write 2, this is not Y. अरे इसका है क्या? I'm first up. So 2 is your minor axis. This is as per ETAP. So all of you know that in ETAP the axes are 1, 2, and 3, and not X, Y, Z. Now, as this is major axis, whatever we do manually, this 3 corresponds to X and 2 corresponds to Y. So that is the only difference, no other difference. Okay. So whatever M3 value you get, you should put as a XX in the Excel sheet. Okay. So that is the only. So this is your M33, or I can say MXX. And this moment is your M22 or MYY. This. Now let's go again. So it's very easy. So 3 is X and 2 is Y. Now you can put the values here looking at this. So let's go to the sheet, and this sheet is designed for by limit state method. So assume the size of the column as, now see, by using the Excel program, it is very easy. Whatever you assume, you can quickly change it as you wish. No need to do the iteration. So let's say this is your, let me take as a 230 by 450. Okay. This is my column size. Grade of concrete, let's say M20, grade of steel 500, and cover to the main bars
40 mm.
Yeah, so it is not 40 mm, it should be 48 mm because stirrups has to be added. In this, the software is saying, I want, if you, this is your column, these are your bars, and there is definitely a stirrups also. Okay, so there is a stirrup which is having some diameter. So the software is asking, I want this distance at the face of the main bar. So our 40 distance plus 8 mm stirrups. So it will be 48.
8.
Now you assume some diameter. Let's start with the 12 mm. And you can assume the steel also. So here you can see the percentage of steel. So generally we don't provide 4 bars for 230 mm width. Let's start with 2. And let's say these are the 4 bars along this length. So you can see 1, 2, 3, 4. As you change this, let's say you make it 3. You can say 1, 2, 3. And along this width, 1 and 2. So it is 2. If you make it 3, then you will see 1, 2, 3. So this way you can change the diameters, numbers. So let's say, now whenever you put any steel, it should be more than 0.8%, because for column, the minimum steel criteria is more than 0.8%. 0.8% is the minimum steel criteria. So whatever steel you provide, numbers and diameter, it should be more than 0.8. Now it is okay. Now let's go, and this is your x-axis, this is your y-axis. Now put the forces coming from the analysis. So you can design, I think, almost 10 columns here in this sheet. I'm interested in single column only. So what is the actual load on column? Ultimate load, 1500. Now there is is written MUX1, MUX2, that is top and bottom. Okay.
Yes,
So
sir.
here you can see MUX1, MUX2,
MUX2.
and MUY1, MUY2. So let's say if you get this kind of curvature, now in our case it is this kind of curvature. This curvature means there is a positive at top and say negative at bottom. So don't get confused with bottom and top. Whatever value you get here, it is forcefully saying MUX1 should be plus or minus, and MUX2 should be plus only. Please, this is the symbolic presentation. So what is our case? Who is plus? 40.
40.
So put that 40 in the plus value here. And who is minus? Here. So you can put plus or minus both the values here, but
Minus
here
20.
it should be plus only. So minus kitna tha?
20.
20. Okay. Now MUY2 should be plus only. So MUY2 plus कौन सा है? नहीं, ये तो 10 minus है ना. 15. 15 is a plus. And ये minus 10 आएगा. Now unsupported length. So let's say your floor to floor height is 3 meters and your beam depth is 600 mm. So how much will be the unsupported length? 3 minus 0.6, 2.4.
0.45, I think.
Huh?
0.45, sir, depth.
No, it is column. See,
Okay.
this is column. I'm saying beam.
Beam.
The beam which is resting on the column, let's assume that the depth of the beam is 0.6. Okay.
Okay, sir.
So this size is nothing to do with this. Now what is the L effective? 0.85 L. So let's say equal to 0.85 into
2.4.
unsupported length. So you get this value. Here also 0.85 into. Now if your building is having shear walls or a bracing within the building, you can call it as a breast. And if there are no shear walls, then you can say unbraced. Now let's assume we have a shear walls. Generally in any building we provide shear walls in the lift zone, minimum at least. So
Yes,
you can
sir.
consider this as a breast design column. Now this is the. Now here you can see that revised section it is saying. That means interaction ratio. It is not calculating because design is not sufficient. Whatever you have provided, the size of the column or steel is not sufficient. So what to do?
Increase the
change
size of the column.
Increase.
Yeah, so increase the size of the column. So I ask you the questions. If you want to increase the capacity of column, what can you do? What are the possibilities you can? How to increase?
Depth बढ़ाएंगे तो
size
सर
of site.
उससे
Increase the size of
MUX बढ़ेगा.
How to increase
Major
capacity? Yes. So there are increase the size of the column. That means either increase B or D.
D.
That is one choice. What is the second choice?
increase
Grade of
percentage of
steel.
reinforcement बढ़ा देंगे.
Increase reinforcement, number of bars or percentage steel. What is the third possibility?
grade of concrete.
Increase grade of the concrete. So there are a lot of choices.
Plasticizers,
No, plasticizer, no. There is no other way. It depends only on the grade. Either it is M20, 25, M30, 35, 40, For high-rise building, we generally use minimum 40 grade. But if it is a low-rise, mid-rise buildings, then you can say 25 to 30. Okay. High-rise buildings are having grades more than 40. 40 minimum and then ahead. Okay, now tell me then, what is your choice? क्या करेंगे?
Size of column.
Now actually we are providing the steel just near to the minimum, isn't it? So see, you can try anything and we can comment on that. Let's go. Okay, you are saying increase the size. कितना लेना है बताओ?
230 into 500. Depth बढ़ा देते sir.
Okay, 500 करेंगे. Shall
Yes,
we
sir.
keep the same steel?
No sir. 16. Diameter of bar 16.
Why?
So
See,
total percent of steel
percentage
is
steel
less
should
than
be more
0.8.
than 0.8. Yes, it should be more than 0.8. That means you should increase. So there are two choices. Either you can now increase the number of bars along this 230 face, but I generally don't recommend to put more than 2 bars if the width of the column is 230, because there will be problem for the reinforcement of beams. Okay, so generally it is not suggested. So either you can increase this. So if you increase, now it is 0.983. So I'm not increasing diameter. I have just increased the numbers first. Let's go here. Is it okay? No.
No sir. 0.9 आ गया. 0.8. Yes, sir.
So let's increase the diameter of the bar. Now your percentage steel,
Increase.
previously it was 0.9, now it is 1.7. Go there. Still it is not satisfied. That means our section is not really sufficient. Okay. So instead of 500, make it 600. And then go again. PT is same. I'm keeping the same. Just go there. Yes, 0.819. Fine. So this is your design, and it is also near to 0.9, or it's good design, we can say. And you can optimize also. How can you optimize? Let's reduce steel. This was 5 numbers. So how much
Four.
number of bars are there? 10. So make it 4. So I'm providing 8 bars. Now check. Oh, not, it is not taking. So that means there is no other way, I think. ये design अच्छा. There is no some other case. Let's reduce these numbers and increase the grade. So let's make it M25. Is it okay? Yeah, it
Yes,
looks
sir.
okay, but you can see the interaction ratio is very near to 0.5. Means you are giving
54%.
so uneconomical hai. So I think previous choice was the better choice.
Better.
But in the, not necessarily it is better, but because it is increasing little still. Now what is the cost and that thing, I don't know. You need to calculate the cost of different options, and then you can say that this option is giving less cost for the columns. Okay.
Yes, sir.
But you can, by looking at the interaction ratio, at least you can understand whether your design is economical or uneconomical. That is the signal. This is the design now. That means you can change size, you can change grade, you can change steel, and you can quickly. So whatever procedure I have told you regarding that interaction charts, okay, the charts are getting developed behind this, within this program. And you need not to bother about key. What is my PU upon FCK? What is my MU upon FCK BD square? Do I need to do the interpolation? Shall I check PU upon PUZ, alpha n, and that whatever procedure I told you, it is there behind this program. So it will directly give the answer. But as I said, I don't recommend to use any Excel programs or RCDC software without understanding the concepts. Yeah, you can study that software as a tool first, then study these manual calculation methods, whatever I discussed with you, and then again use the software. So parallelly you do the things, learning softwares and learning basics. So this is our column design. Now you can say, now I ask you one question. let's say we have a MUX2 as 100 value, okay, and MUY2 also 550, okay. The moments are more in the column from the analysis it is coming, let's say. And now once you go down, then you will see that it is saying that revise section. Now tell me what to change. Size. Let's make it 750. 1.128. So what is the PT? PT is 1.1. Still till 22% you can take the percentage still. So why not to increase the steel? Let's say 6 bars over here. I have increased the size and I have increased the steel also. Now interaction is 0.92. So this way you can control the interaction ratios, capacities and all. Now there are many times there is a possibility that there is a restriction to the size of the column. In that case, you must increase the steel percentage. There is no other way. So as per the architectural requirements, there may be a possibility that architect is demanding certain sizes for his aesthetic purpose or maybe any other reason. Then you can do that. So I hope all of you got the concept regarding the column design.
Yes sir.
Yes, sir.
Any questions?
सर एक्सियल लोड फाइंड आउट कैसे करेंगे ये टाइप के अंदर, यहाँ पर जो आपने एज्यूम किया 1500
1500, हाँ वो क्या उसका क्या
उसको कहाँ से सर्च करेंगे?
ये है ना यहाँ. See, once
अच्छा,
you right click, you will see this window. See,
ओके
you
सर.
take any column, click right click, go to the display.
फोर्स
Not right click, select that column, then display force and display. ये है ना कहाँ गया force trace diagram.
यस सर.
Then there you will get that. You'll got here frame force diagrams, forces here.
Yes sir, understood.
And then you will see this window. In this window, if you click in the component, you'll get this axial P and T.
Okay sir.
And here you will get this 1286. You will get 1500. You need to select this combination also. Load combination 1.5.
Okay,
Yeah, that is the. Anything else? Read these PPTs, whatever I am discussing. So I suggest you take the forces from the analysis from A types. Design one column by manual calculation, design 2-4 columns by Excel programs, and then design the whole building by RCDC software. Okay.
Okay sir.
So you will get, and in RCDC software, you get the calculation reports also. You might have seen that. So that calculation reports are as per the clauses, step by step. So you can read this calculation report, but after manual calculation, what I discussed now, then you will understand each and every procedure here, this one. Okay.
Yes sir.
So is it over now? Any other questions?
सर वो इसमें स्पेसिंग वगैरह का कैसे पता चलेगा सर फिर एक्सेल शीट में?
स्पेसिंग नहीं, that you have to decide. कितना है इसमें ना?
ओके सर.
Spacing of the main bar, it will not give anything. You need to decide. Okay, question
So
पूछे.
मैनुअल में दे रखा था इसलिए पूछ रहा था.
मैनुअल में?
So पीपीटी में दे रखा था ना, वो स्पेसिंग हमने निकाली थी लास्ट में.
Regarding yeah, okay. क्या बोल? Stirrups.
Yes sir, yes.
Yeah, stirrups. For that you need to do it manually.
Yes.
Now generally I tell you, if it is a say gravity load carrying columns, then 8 at 200 spacing is okay. We generally don't provide 300. 200 is okay in all cases, most of the times. And if there is a, and you are using RCDC software, isn't it? Are you done with the column design?
Yes sir.
Yeah, so there you will get the drawings and all detailing also, kitna spacing aa raha hai,
Yes sir.
kitna
Yes
cloth.
sir. उसमें है sir.
Yeah, उसमें है. So अभी क्या है कि this is for just verifying the results and doing smaller projects. You can use this and you can quickly
Yes.
calculate that. So what can you do? I can recommend you, you see your spacing of the stirrups depends on what? Diameter of the bar and dimension
Bar.
of the columns, isn't it?
Yes. Yes sir.
So 16 into diameter of longitudinal bar. So what you can do, you can, for every diameter of the bar, you can calculate this value. So for 20, it is 320, for 12, it is something, and you calculate those. Now for least lateral dimension. So if it is a 230 column size, then it will be 230 here. Then
Yes.
diameter into, yes, 16 into diameter आ जाएगा, और ये 300. We don't provide 300. It should be minimum to 200 generally, practically I say. So ये तो clause खत्म हुआ. Then 200. So you can have that list. You can prepare your say ready reckoner and follow that.
Yes sir. Yes.
एक बार ही करना है.
लेकिन
For any sizes,
तो
you need to
लेकिन
do once only. Yes.
बीम जंक्शन के पास स्पेसिंग कम रहता है.
कम
Top or
रखते हैं.
bottom?
हाँ, तो वो आ जाएगा. I think that will be discussed in earthquake का किया था क्या column का design में? So whenever you do the ductile detailing, we keep the spacing. We will discuss that in the drawing detailing part. Okay. So generally we keep the spacing closer, 150 or 100 near to the beams. So column beam junctions are having more, rather closer spacing of the stirrups. See here closer, here closer, here closer, and then in between different, say 200. So we will discuss that, I think, sometimes in drawing part or something. Okay. Standard drawings and how we are doing that. And please see the drawings given by the RCDC software also. You'll see the total cross section of each column.
Yes sir.
Has then that been discussed? If not, please see that it is there actually in reports and drawings and everything. And we will have a drawing session also sometimes, maybe in some upcoming sessions, where we will discuss regarding the drawings, layouts, cross sections, detailing part, and all this, stirrups, so on. All the detailed part are there actually. So drawing part will be covered sometimes. Okay.
Okay, sir.
Okay
Yeah.
sir.
Excuse me, sir.
Yes, yes.
Sir, in this Excel sheets, do we consider the slenderness effect also?
Yes. We consider slenderness also. Okay. There is one more point. Whatever I have given you this problem, this is a short column. Okay. If the column is having long column, then there will be moments due to slenderness. And they are taken care here. Okay. In this. So if your column is, let's say, long column, let's say I'm having a 5 meter column. So for example, let's say this is your 0.91 and this is okay for this design, 230 by 750 and this steel. Let's make this column as a 5 meter. See, it is saying that revise section. So what has happened here? Why it is asking to revise the section? Previously it was safe for 2.4 meter. अभी 5 meter को fail क्यों दिखा रहा है? Because there are additional moments due to slenderness. Okay.
Okay, sir.
That's why this is now. What can you do? Again, same thing. Either increase the or steel. Let's increase the steel first. Let's make it 20. So my PT is 2.1%. Is it okay? No. That means now generally slenderness is about the minor axis. This is one point. Slenderness is always due to the minor axis. If your width of the column is less, then the slenderness is more. So generally my suggestion for controlling the slenderness is first try to increase the width if possible. Can I make 300 instead of 230? And go ahead and just check it out. See this. That means I have, let's make it 16 again, previous case. let me go again back to my problem. Now this was the failure case. The ratio is 1.7, less than more than 1. Now I will increase first the width and check it out. See this. Getting? So there is a major effect due to change in the width regarding the slenderness. Are you getting this?
Yes, sir.
Yes, sir.
So even for the same depth, for the same percentage steel, the long column is getting satisfied only by changing the width. 230 का 300 करने के बाद, and that too you are having a capacity reserved. It is only taking 70%. So that is the, we can say, how can you design that? That is how can you control the slenderness? Okay.
Okay, sir.
There are some problems. Don't go in this. Actually, there are a lot of things done here, slenderness related. But do you know that there is a SP16? Do you have that SP16?
No, sir.
Yes, sir.
Yes, those who are not having, you can get it from say Google, or we will share you. I will check it out whether it is in classroom or not.
Okay.
So in
So you have
SP16,
shared, sir.
I have shared, I think. Yes.
Yes, sir.
So in that you can refer the design of slender columns also. The procedure is almost same. Whatever I discussed today, there are little calculation regarding the additional moment due to slenderness. That is the case only. Other things are same. So you can go through that SP16. There is a solved problem given there, and you can refer that. But before, you should solve this first. Then you will understand the procedure and where to see what and all these things, charts and everything, and then go for the long columns. And once you understand the concept, then you can use this sheet successfully. Okay. Any other questions?
इसमें सर्कुलर कॉलम के लिए नहीं है क्या?
है, सर्कुलर कॉलम के लिए भी है. शेयर किया है कि नहीं पता नहीं मुझे. We will share all the circular columns and all other columns, whatever sheets we are. In this training program, I am taking only this part just for basic understanding. And once you understand, then you can use this for other part. Okay, please remind on the group tomorrow.
Okay,
I will
sir.
share you all the Excel sheets. Yeah.
Okay.
There is an Excel
Okay.
sheet for uniaxial moment also, but if you do manual, see biaxial, it is okay. Okay.
Good night.
Shall we conclude? Okay, so good night to all.
Good night, sir.
Good night, sir. Thank
Good
you,
night
sir.
and thank you.
Thank you, sir. Good night,
Good
sir.
night, sir.
Thank you, sir.